5 tuple of functions where blah blah blah. And there you see a run of multiplying.
Wait a minute, where's the where? Oh, Jeff.
Right here.
Oh, right.
So that's so.
Oh, I see.
What this is we're doing matrix multiply, but there's some auxiliary functions in there to build matrices.
Right.
So there's a sample run, but the point of this is looking at the code generated. So starting down there in the obvious Lisp code stuff is the code for all these guys. Probably you ought to turn to page 3. Well, there's matrix multiply. Turn to one more page, and there's the inner product. You see the
right.
yeah, one more page.
Yeah.
You'll see that there's the code for inner product.
Right.
And it's inner product 5 because of the flattening of the namespace.
Right.
So that's
so this stuff has gone through.
This has gotten parsed, simplified, not rewritten because nobody's rewriting anything yet.
Right. What about
code generated?
Can you point out something that's happened with the simplification? You know.
Yeah, we'll do that right now.
Okay.
So one thing that you can see has happened. Yeah, is that things have. The reason it got lifted was because of, I'm not sure which it was.
You would have to look at the original.
Original what? Oh, apply to all colon. Yeah.
Yeah, apply to all.
See, the apply to all colon times sitting in there.
So that has
a
to get
simplifier
lifted.
can't guarantee that that's in normal form.
Right.
Because, I mean, at this stage in its development,
Sure.
it couldn't.
Right.
So that whole thing had to get lifted.
Let's see.
Has that been fixed?
Yeah, okay, good
So
question. If you turn 2 more pages, you'll see what happens when the simplifier now knows that apply to all, when applied to something that is a function, is safe to make that thing a function, therefore it doesn't have to get lifted to be a normal
So this is
form.
what
So
you
next
get.
IP5 that you see, 3 pages further,
That's very impressive.
is the code that comes out when the simplifier is smart enough not to lift that thing.
Right.
For example, that's that hash quote FP count.
Oh, that means
do a
function.
phone call, right? That means function. That guy.
Right.
So what I did was I put in some optimizing, some code enhancement stuff that attempts to stick functions in function position in the Lisp expression, and attempts to apply the combining forms when it knows that it can. So if you turn over 2 more pages, you'll see what happens to the code for IP5 when a function of a generated thing. That's what that D416. You see it up there at the top of the page?
Yeah, right.
So that thing says that's a lambda expression or a def fun, in fact. So IP5 is defined to be the function which, when applied to some argument, and I've plugged in there the name D something for defined function.
Right.
It applies a function lambda of 417 in that case, FP plus of apply to all of times of its argument, and its argument there is transpose of the original thing. Okay. So 416 gets bound to a pair of vectors. We can't notice what we might think about doing is actually substituting for that using occurrence of 417, the expression FP trans of 416. Notice that if you turn back 2 pages, you'll see that the code generator has done quite a bit of applying lambda expressions in there. You can't do that one because it's not sure that the function FP trans, when applied to 416, will always produce the same result. In this case, it doesn't matter. There's only one using occurrence, but the code generator is not being that smart. I'm not trying to do that much with it.
Right.
So it won't fold. It won't apply that beta reduction. In other words, because it's not sure that it'll always produce the same result because of I/O.
Right.
So if it could be, if this were something like a constant, then it would stick that constant in there. And let me show you, I got one more quick example of looking at that stuff.
I have two questions about that. Should I wait or?
Doesn't matter.
Okay. One question is there something the rewriter could do to help the code generator? I mean, is there can we leave the R nodes in a particular form that the code generator would find helpful?
To how much the Lisp compiler would do, I don't know. Where Gabriel said that we could find out as much as we want, and these guys already started finding out something about it, making a contact with Lucid. But I don't know. The other thing, the rewrite system can't help too much because some of this stuff is things that are going on in normal form, right? Mm-hmm. So there's not much that can be done.
Yeah, well, speaking of normal form, I thought of my third question. Okay. How do we, so this thing here you say can't be substituted because it may be doing something funny like I/O. When the rewriter is done, every FL expression has the property that it's in normal form, so it can't do I/O. Now, is the fact that you're doing some optimizations here meaning that we don't have the normal form property?
Well, we don't.
Did I say that clearly enough?
Yeah. Has got transpose applied to the argument of this guy. Right?
Yeah. And now, where did that come from? What was the R node that corresponded to that?
It was a composition.
Oh, it was composition as opposed to application.
Yes. I see. And composition got reduced there. Let's see if we can find it earlier on back here. Yeah. See, here was the composition of this whole list of stuff, and transpose. So the composition is being applied to that thing. Lambda x, that thing of trans of x.
Right.
So that's where that thing got done. And we have to know that we can do that, and particularly we have to know that comp can't do any I/O, and so that's a safe thing to do.
So you've eliminated the composition by replaced it by an application.
Right. We've applied the composition at code generate time.
Right.
So we've changed F circle G into lambda x of F applied.
Right.
Simple example. So if you turn the page, there's the code that comes out. You'll have to turn 2 more pages to see the Fibonacci program. So on the very last page is the program.
Right.
So there it is. It's tucked up there, not easy to read at all.
Right.
F, where F is defined to be blah, blah, blah. Okay, that's applying K to things and so forth. Then you get this Fibonacci code on the last page, which is about the way you'd write it in Lisp, except for the fact that you wouldn't do this labels business.
Right.
So here you'd have Fibonacci is a right. We're defining Fibonacci to be lambda x, a conditional.
Right.
If something's equal to something, that is, if the argument's equal to 0, if that produces false, you see we have one extra level of testing because our functions return. All those guys got expanded.
How many different sorts of rules or strategies are you using right now to iron out things?
I think currently there are 5 things that get applied at generate time. There's the composition, construction, conditional.
Okay.
So you notice all these conditionals are in here too, in this version of the thing.
And these are like phases. I mean, you go over the whole thing into one thing, and you go over the whole thing into another.
No. At the place. Next time I'll actually show you the code that does this, the code generation algorithm. So when you're required to produce an application of the left-hand side to a right-hand side, you check the left-hand side and see if it's something that can be applied. You check the right-hand side to make sure that it's in normal form, so that it won't change the semantics if you distribute multiple copies in, for example. Okay. And if both those things pass the test, then you actually apply like a Lisp macro to expand the Lisp code, to actually do the application of the combining form at runtime. But now some of these aren't combining forms. So for example, ID is in there. So you'll see that Ed and I were thinking, if you have ID applied to something, well, the rewrite system will knock that thing out.
Right.
But that's not so, because what if we have comp applied to the pair, something and ID. Well, that may be a bad example. The rewrite system may get that guy. But what if then I get rid of the lambda expression, I do beta reduction at code generate time. And that's where almost all of this savings finally comes from.
When you say no matter how many times it's generated, you mean in how many different places, not if you evaluate it and then evaluate it again, right? I mean,
Right. Oh, yeah. Right.
okay.
That's right.
That's why I listed never list.
Yeah, that's why that page is
Serve page and all.
right. Right. That's right. So there's two things. If, as a matter of fact, we happen, it's true about FP trans of anything. If you transpose an argument, then if you start all over again, you know, and reevaluate that expression, you have to get the same thing because transpose can't do any I/O, can't have any side effects. Right? So even if there'd been more than one using occurrence of this ampersand 417, we could have substituted that expression in there and gotten rid of the closure, the lambda 417.
Right.
That wouldn't have been a good idea.
But now it becomes a question, is that a good idea or not? Probably not. That would mean you'd in Lisp at runtime, you'd have to transpose a matrix twice.
Right. Right.
Rather than, so that's, some of these things are not a good idea to.
Yeah, it's really hard to
substitute.
get the right strategies
Yeah.
for these things.
So I have two issues. One issue is with this equal test to false. Yeah, you're looking at it.
Where are we?
Very last page.
We could do something about that in the rewriter. In particular, instead of having FP cons, or cond, which tests to see if the first function is false, and branches to the second arm, we could have tests to see if it's nil. So we could change cond to cond1, and cond1 acts like the Lisp cond, and then we could get rid of this equal false test if we wanted to. So we could handle that in the rewriter if we wanted to, and it may be worth doing.
We might as well wait though until we move to C before we start doing that stuff.
Yeah, maybe so.
Right.
But we have something we can do about this,
Right,
so
sure.
we're not in terrible shape.
The cost of testing, an EQ test is minimal anyway. Testing for nil is going to be a nanosecond faster or something. So.
Yeah, I don't think that'll help a lot at all. Here's something that will help looking at that exact example. Why didn't that list true and one get substituted in there for, so here's the form of this thing, lambda, the
Right.
DAT 813.
Right.
So this whole thing's a conditional. But the argument here of, I'm pointing at the wrong thing, aren't I? That's the argument of the factorial. I want to see why this T1 thing didn't get. Oh no! I'm sorry. That's nonsense.
Why does the list?
There is no.
The list of D.
That's what I'm looking for, right. Right. Why didn't the list of D813 and 1 get substituted in? So look at that nested, that innermost lambda. So it says lambda 818.
Right.
Do factorial, that's F0, factorial of FP sub of 818.
Mm-hmm.
So what happens there? 818 gets bound to the list, whatever 813 was, and 1.
Right.
And then we evaluate that expression. Now that's something that I'm going to, as a matter of fact, do that next. Currently, I don't know that guy's a constant. It says I'm the list, and whatever 813 evaluates to, and 1. In Lisp, that wouldn't necessarily be a constant, because D813 could get assigned by somebody.
Right.
Because it's just a symbol, just a generated symbol. And so it depends how many times if it gets evaluated in some context, it could be one thing, evaluated in another context to be something else.
Right.
We don't have any side effects that will change that value.
Right.
So my predicate the test to see if something's a constant, I'm going to change. So if the thing's a dot log. don't move your hand. You'll spoil the whole tape. You'll have to start all over again.
Yeah.
Yeah, I will eliminate that, right. The interesting thing is, and this is something we have to ask, John or whatever his name, Gabriel, John, is when you write the thing this way, so I'm reading level, right, all the definitions are supposed to be local, and just whatever expression gets returned.
I see. So that's
And it's slower.
This construct is in
Page down a little bit there, Paul. See if somewhere I had a.
Were you?
Well, maybe I didn't. Maybe I didn't save it in that log. I don't know. I guess we're not gonna.
No.
We're gonna see that. That was an interesting thing there. That was the result of seeing what Common Lisp did with fun calls versus functions in function position. And fun calls, it just absolutely blew up on, generated an enormous program.
Really?
Thousands of lines.
Yeah. The Lisp compiler just is not expecting our
order.
kind of higher order stuff.
Right. That's right. Okay. That's
probably the C compiler isn't either. I mean, it's...
Well, but
C compiler shouldn't matter.
yeah, I mean, we're not counting on the C compiler to do anything for us, right? In that regard.
I have a question. Does the Lisp compiler recognize these as constant functions?
which
Like FPMO
is constant functions.
I mean, can you declare to it that these functions are primitives?
Declarations you felt.
I have the foggiest idea. I don't know that.
Alex has
anything at
already
all.
put a lot of declarations into the primitive definitions. And,
Didn't seem to do much.
yeah.
Declare fix now.
Right, I didn't see a lot of that, but I wasn't looking closely.
Okay, so that really looks good. I mean, I'm just amazed how far we've gotten. You know,
Not any rewriting.
Tupling. But I guess this one doesn't. We'll have to learn about this. Actually, we're not far off now. I mean, shoot, if we're a factor of 3 and we know some things to do.
right.
I think what we need to do is
I mean, if we think about the prototype compiler, how bad are we, in generating C code? I mean, Lisp, sort of screws up in a number of ways here that presumably the C compiler won't. Or am I just...
Which C compiler?
But
I mean, Lisp is just a little bit closer to our intermediate form. We still
Yeah.
have the notion of functions and so on and so forth. And I don't think it's like Lisp is really screwing up. It's just not ready to handle what we're giving it.
right.
So,
And we're just going to have to handle a lot more detail. It's
it'd be
C.
an awful lot more work to generate
Right.
C code.
But we already have a good start because we have the for construct and we have the bind
right.
operation, and those are both
Very C oriented.
and they
no, but you can't. The programmer can't write it.
Yeah, right.
And the rewrite system is the only one that can write it.
Right, and
And it isn't
doesn't
doing much.
it isn't writing it.
Let's talk about the status of the rewrite system.
well, the rewrite system is supposed to be ID.
Fixed multiply thing. He said it is. So I've used the. Maybe I won't use. Oh yeah.
This is something that we took off his slide. So Pete gave a talk and he had this program on his slides that he hadn't run.
Right.
So we just transliterated his program in
Right.
Hope into FL. And what we're about to see now is this.
Is the transliteration.
Right, the transliteration
Right.
of the program as it came from
Hope.
From Hope.
Right.
Okay, so now I have to try to
What's
get
it
his
all?
mistake in, right?
Yeah.
Yeah,
Right.
you're missing a paren.
That wasn't his mistake.
Right.
It's your mistake.
That was a syntax error. Ooh, we can use two colors to.
So this is an error that really our parser would. No, the parser didn't find the
Well,
error.
the way we found this error was we ran the program,
Yeah.
and we got an error message, and the error message said something like cons was being applied to a function, and we knew that couldn't happen.
Right.
Now our type analyzer and our rewriter, when they're all working,
It would have.
probably would have caught this and said cons is being applied to a function.
Right.
You know, here's a bad thing.
I'm not sure I can write it the way it was wrong.
Yeah, all we changed were some parens.
Yeah, I know. Well, so
Well, I think.
Okay, so-
Write it right, and then we'll put in red to make it wrong.
well, no, I don't want to do that. I want to write it wrong.
Okay.
And then make it right. Oh.
I understand is,
So you get this.
do you have double A or double alpha as an operator?
Oh, yeah.
Just be alpha.
That's just right. So you get this
Pete made that same
construction.
mistake too. It's interesting.
You get. Oh.
Was that the mistake?
Okay. So now you get a construction.
Yeah, you're missing some parens.
Yeah, so clearly something is wrong, right? We shouldn't apply cons to alpha.
Yeah, so
So
there ought to be
alpha
a
must
left.
be being applied to something here.
Right, so there ought to be a left paren by the alpha.
All right.
Does colon associate left?
Change colors.
Yeah.
Colon associates left, yeah.
No, I mean, yeah. Okay, good.
Okay, so there's a correct program.
It is. Okay. Now.
Now what does it do?
Yeah. What does it do?
So it says lambda 2 matrices, M1 and M2. Now do this, evaluate this object, of course. Now we use lambda. So you transpose the second matrix.
Right.
You apply curry to inner product,
Right.
and then you apply that function to all the rows of M1.
Right.
So
So you have a sequence of functions, each of which is an inner product.
each of which is ready to take
Yeah. The
other
second argument.
of that guy.
But now.
You apply that function to every one of the. But now, what did he have missing? That was
So wait a minute. I still am having a little trouble understanding that damn thing because look, I mean, here is one of these things, right? It's a one of these inner product things, right? So that's this, right?
That's the right.
And now when I apply that to a particular row of this matrix,
Shouldn't it be dot com?
I'll get I see, I'll get the whole row.
Right.
And so I just want to do that to every row.
Right.
Now I understand.
Right.
Thanks.
Yeah, what Pete had wrong, I think, was that he had. That's what he had.
So let's see. So you'd apply. Yes.
That's
Oh, I see. So cons is getting applied to a function. Sure.
right. And the error message we got said cons
Right.
arg1
Right.
function.
Right.
And so we knew that cons had to be applied to a sequence of functions. And
So that was kind of a plus for our exception system. that
Yeah,
really-
yeah,
Yeah.
yeah. And so when we had the meeting, we were just saying, move the printer over, and Pete was saying, no, that won't work, that won't work. I said, so we tried and it worked.
So it works. It actually does. So it gives you answers that you didn't know you would get.
Yeah, I mean, that's a kind of I'll surely wave my hands without trying. Say when. Well, we've been working on this language called FL for a long, long time. And the reason we've been working on it for such a long time is that our goals are very ambitious. We're trying to produce a language that has three major properties. First one is that it's very powerful, that you can write a program in perhaps a tenth the time that it would take you to write a program in any language today. Second property that we want the language to have, and we hope it does have, is that it's a universal language, that it's a language that you can write any program at all in, a number crunching program, a graphics program, a compiler, any program, a database program, great variety of systems programs and things like that. And finally, perhaps the hardest of our three goals is that we want the language to be very fast. That is, we want, having written a program, it should run as fast as a good FORTRAN program or a good Lisp program, depending upon whether it's a sort of a regular kind of program or a list processing program. And it's taken us many years to sort of design the language, and we're now trying to prove that we can meet, at least to some degree, these very ambitious goals. So we have a system right now which will compile and run FL programs, but it is our, what we call our bootstrap compiler, the one that we will use to compile our compiler, as we intend to write the compiler in FL, and the compiler we're working on now will accept an FL program and produce a Lisp program, and then we can run that. If we put our FL program for the compiler into this bootstrap compiler, we'll get out a Lisp version of the compiler, which we can then use to compile itself. And the compiler that we write in FL will describe how to translate FL programs into C programs, so that when we have finished compiling it, we will have a C compiler for FL. And
Can I hold 1 minute? I'm getting really big.
So the reason we've worked so long and hard on this FL language and compiler is that programming is the real bottleneck in the use of computers. That you have your choice today of writing a program in a language like C, which will take you a very long time because you have to deal with every tiny little detail of what you're doing, and you can't think in large terms at all. Or you can write it in Abe Peled or perhaps Lisp, and if you do that, it'll perhaps be a lot faster to write the program, but it's very likely the program will run very slowly when you're finished. And so there are various languages that you can prototype programs. You can write the program quickly, but you wind up, after you've checked out that the program actually runs, you then have to go back and rewrite it and see if you want to use it a lot, because it runs so slowly. So, so what we're trying to do is to break that bottleneck, so that you can write a program very quickly and have the program that you write be an actual production program.
Okay. Do we want to get John or somebody? Wait until I'm up to speed. Sorry.
So in order to achieve the power that John talked about, it's important that the programming language have elegance and simplicity, so that when one programs, they can express powerful ideas simply. And a very important part of powerful programming is simplicity of semantics. So it's important that the language provide something that's easy for the programmer to understand. We try to achieve that in FL by having functions be the basic unit of programs, and all a function does is it maps one particular object into another object, the answer. And keeping this simple model in mind hopefully makes it easier for the programmer to express his programs. Furthermore, having a nice simple semantics enables us to easily determine when two different forms of a program are the same, and hence this gives us a strong algebra of programs, which enables us to transform one program into another easily. And the simple semantics gives us an opportunity to easily determine if two different programs are equal, and hence hence we can transform one into a hopefully faster running second version.
All right, this is about 10 seconds about rewriting, because it's one of the parts of the FL implementation project which hasn't gotten very far yet. One of the most important.
Let's do that again. You don't really
Okay.
want to tell me how long it's going to be.
Well, no, that's the tape lead, and you're supposed to edit that out.
Right. But I still need the word rewriting in the beginning.
Okay.
And talk up a little bit.
All right. One of the aspects of the FL.
You have to settle first. Okay. That's right. Just
I should have my head in one of those metal vices. Photography in the 19th century. Okay. One of the big differences between the FL compiler that we're beginning to build now and most conventional compilers is that the core part of compilation, following parsing and before code generating, is going to consist of an algebraic rewriting system. One of the big challenges with FL is to try and get programs to run fast, because if you examine their structure as an application programmer writes a program in FL, they're full of powerful and clear but apparently inherently inherently slow constructs. And the challenge of compiling FL is to transform FL programs, retaining their semantics exactly, but transform into a form which is much more difficult for a programmer to understand, but is easy to compile and run fast. And the mechanism by which we're planning to do this is through a rewriting system, which will recognize certain patterns and opportunities in the code and mathematically transform pieces of program, preserving semantics exactly into another form. And that's something we're beginning to do now, but it's quite an open problem for a number of reasons. And FL, the structure of the language, is slightly different from other models that we've looked at so far. So we're in the early stages of playing with our matching and rewriting system to learn a little bit more about the real nature of the problem we're trying to solve, and how good we have to be at various parts of it.
Give me that so again. So we're.
So.
Wait, plug it first.
What did I say? Does anyone
So
remember?
we're trying to get the rewriting rules.
So at this point, we're really trying to learn more about our problem so we can solve it better. We have a preliminary matching and transformation system, and we're exploring strategies for using and improving that.